Okay, this chapter is a multiple regression, but here we will talk about the inference. So statistical inference, we already know the statistical inference. When we collected a sample, we gonna estimate our population mean, but using the sample mean, right? So then we try to infer what would be the population mean. So what we calculated from the sample is actually the sample mean. I know the sample mean will not be exactly same as the population mean, so we just estimate and get some infer. Okay, my population mean will not be exactly same as the sample mean, but population mean will be around. In other words, actually, our sample mean will be around the population mean, right? So how far they can be separate. So we will talk about that kind of things. So same thing we can do. We estimate the all the coefficients. So how much the education affected our salary, that is the coefficient. Is it 2 or 3? It depends on the scale, but anyway, that will give you the if the education 1 year education increased, how much my salary increased. That's the coefficient. But that coefficient is also calculated from the sample. So we are trying to estimate what would be the population coefficient. Because what we calculate the beta 1, beta 2, beta 3, those parameters are from the sample. So same thing we can do. We will talk about what would be the population parameter will be. So we can do the same thing we did in the mean and standard deviation from the sample. We can do the also same thing to parameters. So hypothesis testing about the population parameter. So we can figure it out. The parameter beta 1 is actually 0 or not. So later I will talk about why the 0 is important here. And then also we will talk about the confidence interval of the parameters also. Okay, sampling distribution of the OLS estimator. So we calculate the estimator. But that estimators are random variable because our samples are random. So we know what is the expected value, what is the variance, but we have to know the distribution, right? We need to know their distribution. Here the distribution is the distribution of expected value and distribution of the expected value and distribution of the variance. Okay, so to get that, we have to have some assumption about the distribution of error. So we will assume, I think we already mentioned about this, follow the normal in the simple linear regression. So for sixth assumption, this is a multiple linear regression assumption. 6 is the normality of the error term. So there is all error here and there, but that error follows a normal distribution. And then we already talked about this, right? So this sigma standard deviation or the variance is not the factor of the variable x1 or x2 or x3. Okay, so this is a kind of assumption. We assume our error or the residual or the error term that follows normal distribution. So it's not always higher tendency to have a positive or tendency to the negative. So we have a same equal chance to have a positive error and negative error. And also the distribution, the probability, the standard deviation or variance are the certain number, and that number will not change by my variable x, I mean the independent variable. So which means it's everywhere is the same variance. So basically the error term is the sum of many other unobserved factors. So there's a lot of different factors, but we didn't collect that data, so we don't know that all the mixed up the different some unknown factors, that is the error term. So that's why our model cannot capture that part. Some of the independent factors which we don't capture should be the normally distributed by central limit theorem. Central limit theorem is, if we just adding up to the random variable, that random summation of that random variable will follow the normal distribution. That's why, since the error term is the summation of many different unknown, here unobserved, that's why we don't have a factor that. Some of these independent factors are normally distributed, so we can assume our error term is normally distributed. Okay? So question is, can we assume that way? So how many different factors? Do we have enough number of factors? We don't know. This is an unobserved factor, so we don't know how many unobserved factors out there. And possibly very heterogeneous distribution of the individual factor. So if your individual factors are all different, and then if you add up the just few number of the factor, maybe that the summation may not follow the normal distribution, right? So that's why we call this is assumption. And also the independence of the individual factors also affect our result. However, we will assume, okay, so we assume there is a large enough number of unobserved factors. Therefore, we can assume our error follows normal distribution. So normality of the error term is an empirical question. It should be close to the normal, right? Maybe not exactly the normal. But in many cases, normality is questionable or impossible by definition. So this is kind of the problem. However, we will assume that this normality, normal distribution of the error term, and then we can talk about the inference of my regression model. So some examples where the normality cannot hold. Wage, non-negativity. Non-negativity, when there's a the normal distribution looks something like this. But what if there is a zero here? So distribution usually skewed because you cannot have a less than zero. Usually looks like this, right? So this cannot be a normal. That's non-negativity caused the non-normal form. Number of arrests take on the small number of integer value. So number of arrests is if the number of arrests is like 75, 125, that big number, then you can assume, right? This bar chart can be similar to the normal, right? However, when the number of arrests is just 1, 2, 3, 0, maybe it will not getting close to the normal. And again, you cannot have a negative number of arrests either. So same problem here. Number of arrests has a non-negative problem also, and this one has just a small number of integer value. And unemployment, this is a 0 or 1. It cannot be, the outcome is only 0 or 1, right? How can it be a normal distribution form? Impossible. So some case normality can be achieved through the transformation of the dependent variable, something like a log wage. So later we will see the example. So we take a log on wage and change to the log into the wage into the log form, and then we can assume the wage, our error term can be a normality. If normality is the assumed, it doesn't matter if it has a weakness or not, but if we assume our error term is normal perfectly, then this OLS is our best unbiased estimator. So that's why we keep using this least square method. So this is just the name of the terminology. So the assumption we used in the previous section, multiple regression for estimation, that's the assumption is 1 to 5. That's what we call this Gauss-Markov assumption. But including the sixth one is the classic linear model assumption, which one, the sixth one, is normality, right? So normal sampling distribution is under the assumption of this thing. My estimated beta j, this is the estimated coefficient, will be follow the normal distribution of this is population beta, right? This is from population. So actually, which we don't know. This is a sample. So this is a beta from sample. This is a population beta. Will follow this way. So if you just change, what is this form? This is just like x minus mu over sigma, right? It's calculating z value. So z value is always follow the standard normal, which is a normal distribution. Mean is 0, standard deviation is 1. Scale is 1, or it's the same. It's the same meaning. So this is not like a new formula. This is just z value formula.